Hello everyone. Let's continue from where we left off last time. So we had finished the first three sections. The third section just discussed about the different types of models on which prompting is used. So it is sort of a survey on current pre-trained language models, but from the perspective of prompting. So let's now have a look at prompt engineering. So prompt engineering is the process of creating a prompting function, which we discussed earlier, that recalls in the most effective, uh, that results in the most effective performance on the downstream task. So, in many previous works, this has involved prompt template engineering, like we saw in the case of sentiment analysis, where a human engineer or algorithm searches for best template. As shown in the prompt engineering section of Figure 1, one must not consider the prompt shape and then decide whether to take a manual or automated approach to create prompts. So the prompt shape, as noted above, there are two main varieties of prompt. You have close prompts, which are fill in the blanks of textual strings, and prefix prompts, which continue a string prefix. Which one is chosen will depend both on the task and the model that is being used to solve the task, right? So, for instance, if you want to have train the model on fill in the blank type tasks, then you of course use close prompts. In general, for the tasks regarding generation or tasks being solved using standard autoregressive language models, prefix prompts tend to be more conducive, and as they mesh really well with the left to right nature of the model, because once you see all the context on the left, then you start making predictions. For tasks that are solved using mass language models, close prompts are a good fit, as they can closely match the form of the pre-training task. So full text reconstructions models are more versatile, and they can be used with either close or prefix prompts. Finally, for some tasks regarding multiple inputs such as text pair classification, prompt templates must contain space for two inputs or more. So if you have more input samples. Then template engineering. Perhaps the most natural way to create prompts is to manually create intuitive templates based on human introspection. For example, the seminal Llama dataset provides manually created closed templates to probe knowledge in language models. Brown et al. Create manually crafted prefix prompts to handle a wide variety of tasks, including question answering, translation, and probing tasks for common sense reasoning. Then Schick and Schutz 2020 and 2021 A and B use predefined templates in a few short learning setting on text classification and conditional text generation. So manual template, an example would be uh, you have the sentence X and then you add I thought it was, and then you add a blank Z. So X would get filled in by your input, and this is for sentiment analysis. So if this is say for movie reviews, X might be I really liked that movie and I thought it was, and then it would get filled in. Then automated template learning. While the strategy of manually crafting templates is intuitive and does allow solving various tasks with some degree of accuracy, there are several issues with this approach. Crafting and experimenting with these prompts is an art. Oh, sorry. Creating and experimenting with these prompts is an art that takes time and experience, and for complicated tasks like semantic parsing, and even experienced prompt designers may fail to manually discover optimal prompts. To address these problems, a number of methods have been proposed to automate template design. In particular, automatically induced prompts can further separate into discrete prompts, where the prompt is actual texting, and continuous prompt, where the prompt is instead described directly in the embedding space of the underlying language model. So one other orthogonal design consideration is whether the prompting function is static or not. So does it give the same output for the same prompt, or dynamic, where it generates a custom template for each input? Sorry, by static they mean that does it give the same prompt template for each input, or dynamic where it generates custom templates for each input. Both static and dynamic strategies have been used for different varieties of discrete and continuous prompt as uh, will be discussed below. So let's have a look at discrete prompts first. So I hope you understand what discrete prompts are. Discrete prompts are, as we saw earlier, prompts which are actually text. So like the one I wrote here, a soft prompt would be, or what they call a continuous prompt, would be where you don't really have tokens. You add that in some deeper layer of the neural network where the text has already been converted into a vector. So your prompts are also just a vector in the same vector space. Then discrete prompts. Discrete prompts, aka hard prompts, automatically search for templates described in a discrete space, usually corresponding to natural language phrases. And then there are some methods. So for prompt mining, you have mine Jiang et al.'s mine approach, where it is to automatically find templates given a set of training inputs X and outputs Y. The method scrapes a large text corpora like Wikipedia for strings containing X and Y and finds either the middle words or dependency path between the input and output. So frequent middle words or dependency paths can serve as a template X then middle words Y. So if it sees say for instance the words Tesla and Model X a lot of times with the words is a car is made by, so it might learn Model X is made by Tesla. Then for paraphrasing, paraphrasing based approaches take in existing seed prompts which are manually constructed or mined and then paraphrase it into a set of candidate prompts, then selects the one that achieves the highest training accuracy on the target task. The paraphrasing can be done in a number of ways, including using round trip translation of the prompt into another language and back, using replacement of phrases from a thesaurus, or using a neural prompt rewriter specifically optimized to improve accuracy of systems using the prompt. However, Haviv et al. 2021 perform paraphrasing after the input X is input into the prompt template, showing allowing a different paraphrase to be generated for each individual input. All right. So for paraphrasing, you have all these different methods which we have discussed here. You can do back translation, which is say you translate the sentence into French, then from French back to English. So some words would be replaced by synonyms and are rewritten. Then you can do replacement of phrases using a thesaurus. You can use a neural prompt rewriter, which is optimized to do this. But all of these are doing this on the prompt itself. While the approach mentioned here by Javi et al., instead of doing this directly on the prompt, what they're doing is they're doing this on the filled prompt, not the answered prompt, but the filled prompt. So where you just have replaced this X with the correct input, and then you pass that into a paraphrasing system. Then you have gradient based search. So Wallace et al. Applied a gradient-based search over actual tokens to find short sequences that can trigger the underlying pre-trained language model to generate the desired target prediction. This search is done in an iterative fashion, stepping through tokens in a prompt. So built upon this method, Shin et al. Automatically search for template tokens using downstream application training samples and demonstrate strong performance in prompting scenarios. Uh, so a gradient based search, I'm not really very familiar with gradient based searches. So let's just have a look online. What is a gradient based search? Hmm. There doesn't really seem to be a lot. Maybe I'll just go over that paper itself. Um, I'm just going to go into the references and pull that paper out and then let's see, maybe the abstract can help us understand what gradient-based search is. Sorry for the delay. I should have read these sections earlier, but I really just like reading the paper in front of the camera first. So it also shows how I understand these works. So this paper. So they have a gradient guided search over tokens which finds short trigger sequences. All right. Um, so let's have a look at where they define this. So the trigger algorithm. We first choose the trigger length. Longer triggers are more effective while shorter triggers are more stealthy. We initialize the trigger sequence by repeating the word the subword or a character We can iteratively replace the tokens in the trigger to maximize the loss for the target prediction over batch of example. To determine how to replace the current token, we cannot directly apply adversarial attack method from computer vision. Instead, we build upon hot flip, a method that approximates the effect of replacing a token using its gradient. All right, so essentially, just from the high level idea which I got of what they're trying to do is they're trying to find samples which break the model, and to do that, they're using some seed words to initialize their trigger, and then they're trying to find the trigger sequence which maximizes the loss. So they want to get uh, okay, they want to minimize the loss for a target prediction over the batch of examples. And so why would minimizing the loss be effective? So they are replacing the token in some fashion, and then I'm not entirely sure how this works, but uh, the token replacement strategy, I guess, is pretty clear now. They are going to find words and replace them using this hot flip strategy, which would uh, using the gradient which this method approximates. And then that method then helps to pick up tokens through which you can minimize the loss for the target prediction. Maybe if I find some good resources, I'll add them down in the description. Next, we have prompt generation. Other works treat the generation of prompt as a text generation task and use standard NLG models to perform this task. For example, Gao et al. Introduces sequence to sequence pre-trained T5 into the template search process. Since T5 has been pre-trained on a task of filling in missing spans, they use T5 to generate template tokens by specifying the position to insert the template tokens within a template and provide training samples for T5 to decode template tokens. Ben David et al. 2021 proposed a domain adaptation algorithm that trains T5 to generate unique domain relevant features for each input. Then those DRFs can be concatenated with the input to form a template and can be further used for downstream tasks. So this is just generating the prompt directly from a text generation model such as T5. Then you have prompt scoring. Davison et al. Investigate the task of knowledge-based completion and design a template for an input using these head relation tail triples using language models. So this is the task of knowledge-based completion, which would be, I guess, to fill in your knowledge graph. They first handcraft a set of templates as potential candidates and fill the input and answer slots to form a filled prompt. They then use a unidirectional language model to score those filled prompts, selecting the ones with the highest LM probability. This will result in a custom template for each individual input. So this covers all our discrete prompts. And now let's have a look at the continuous prompts. So because the purpose of prompt construction is to find a method that allows an language model to effectively perform a task rather than being for human consumption, it is not necessary to limit the prompt to human interpretable natural language. Because of this, there are also methods that examine continuous prompts, which would be soft prompts, that perform prompting directly in the embedding space. Specifically, continuous prompts remove two constraints. They relax the constraint that the embedding of template words be the embedding of natural language, so like English words, and then remove the restriction that the template is parameterized by the pre-trained language model's parameters. So what do these mean? The embedding of the template words, if you had a discrete template, then it would of course be the embedding of the natural language like uh, English words, right? But since these models have seen a lot of data, when you use soft prompting, you might get an embedding which does not really correlate with English words, but works really well. Secondly, you remove the restriction that the template is parameterized by the pre-trained language model's parameters, because now it is not, because your template is no longer going into the language model with the input text and getting converted into the embedding. It is getting directly added after the input has already been converted into an embedding. So now let's have a look at the methods. We have prefix tuning. So prefix tuning by Lee and Liang 2021 is a method that prepends a sequence of continuous task-specific vectors to the input while keeping the language model parameters frozen. Mathematically, this consists of optimizing over the following log likelihood objective given a trainable prefix matrix M5 and a fixed pre-trained language model parameterized by phi. So you maximize the probability of yi given h less than I and the model parameters and phi, which would be the prefix matrix M of phi. So in equation 2, h less than I is a concatenation of all neural network layers at time step I. It is copied from M phi directly if the corresponding time step is within the prefix. So hi is m phi of I. Otherwise, it is computed using the pre-trained language model. Um, so I guess this just means that once you compute it, it is there in the trainable. Okay, so this just means that for some previous time steps which are within the prefix, you can directly pick them up from M of phi because it is the trainable prefix matrix. But for some others, you cannot. So that is computed using the language model. So experimentally, Lee and Liang 2021 observed that such continuous prefix based learning is more sensitive to different initialization in low data setting than the use of discrete prompts with real works. Similarly, Lester et al. Prepend the input sequence with special tokens to form a template and tune the embeddings of these tokens directly. Compared to Lee and Liang 2021's method, this adds fewer parameters as it doesn't introduce additional trainable parameters within each network. Uh, Kelly et al. I'm really sorry if I mispronounced his name, train a vision encoder that encodes an image into a sequence of embeddings that can be used to prompt a frozen autoregressive language model to generate the appropriate caption. They show that resulting method can perform few shot learning for visual language tasks, such as visual question answering. Different from the above two works, the prefix used in Kelly et al. 2021 is a sample dependent, namely a representation of input images instead of task embedding. So, just to go over all the works mentioned, in the Lester et al. Paper, they prepend the input sequence with special tokens to form a template and tune the embedding of these tokens directly. So instead of doing the work which we saw above, this adds fewer parameters as it does not add these tunable parameters within each network layer. It just does that into the input sentence. So it is uh, tuning the embedding of these special tokens only. And in the simple Kelly et al. Work, they have a vision encoder, and their entire task is for vision language conversion. So tuning initialized with discrete prompts. So these are methods that initialize the search for a continuous prompt, uh, using a prompt that has already been created or discovered using discrete prompts. For example, Zhang et al. First defined a template using a discrete search method such as autoprompt. Uh, Autoprompts. Okay, so this is uh, a possessive apostrophe s here. Autoprompts initialize virtual tokens based on the discovered prompt, then fine-tune the embedding to increase task accuracy. So they get a initial accuracy, initial embedding based on a discrete prompt, which they then optimize. This work found that initializing with manual templates can provide a better starting point for the search process. Kane and Eisner proposed to learn a mixture of soft templates for each input, where the weights and parameters for each template are jointly learned using training samples. The initial set of templates they use are either manually crafted ones or those obtained from prompt mining. So all of these methods just show that you are initializing your process using discrete prompts. And finally, in the Hambad Zumian et al. 2021's work, they introduce a user of continuous template whose shape follows a manual prompt template. So finally, you have hard soft prompt hybrid tuning. Instead of using a purely learnable prompt, these methods insert some tunable embedding into the hard prompt template. So Liu et al. Propose p-tuning, where continuous prompts are learned by inserting trainable variables into the embedded input. To account for interaction between prompt tokens, they represent prompt embeddings as the output of a BILSTM. P-tuning also introduces the use of task-related anchor tokens such as capital and relation extraction within the template for further improvement. These anchor tokens are not tuned during training. So in this work, they have some task related tokens, anchor tokens whose template are which are present within the template. And so, for example, in relation extraction, you have the token capital, and you make sure that these anchor tokens are not tuned during the training. So your template as a whole gets tuned, but their embeddings get tuned, but the anchor tokens do not. For Han et al. 2021, they proposed prompt tuning with rules, which is PTR, where they manually crafted sub-templates to compose a complete template using logic rules. So to enhance the representation ability of the resulting template, they also insert several virtual tokens whose embeddings can be tuned together with the pre-trained language model parameters using training samples. So the template tokens in PTR contain both actual tokens and virtual tokens. Experimental results to demonstrate the effectiveness of this prompt design method in relation classification tasks. So this is sort of both hard and soft prompt hybrid tuning. Both are being used here. Then let's move on to the fifth section, which is again answer engineering. So far we were doing prompt engineering, but once the model fills in your prompt and gives you a filled prompt, how do you decode the answer out of it? So let's have a look. Answer in contrast to prompt engineering, which designs appropriate inputs for prompting methods, answer engineering aims to search for an answer space Z and a map to the original input Y that results in an effective predictive model. Figure 1 of answer engineering section illustrates two dimensions that must be considered when performing answer engineering. So you want to decide the answer shape and some answer design. For instance, some common uh, granularities are token level. So one out of the tokens in the pre-trained language model vocabulary or a subset of the vocabulary. Then you have a span, a short multi-token span. So they are usually used together with close prompts, and then you have sentence, which are usually in autoregressive tasks. So for prefix prompts. In practice, how to choose the shape of an acceptable answer depends on the task. Token or text span answer spaces are widely used in classification tasks, but are also used in tasks such as relation extraction or NER. Longer phrases or sentential answers are often used in language generation tasks, Radford et al., which I believe is a GPT paper, but also used in other tasks such as multiple choice Q&A, where the scores of multiple phrases are compared. So now design methods. So if you have the you want to design the answer space Z as well as the mapping to the output space Y if the answers are not used as the final outputs. So manual design. In manual design, the space of potential answers Z and its mapping Y are crafted manually by an interested system or benchmark designer. There are multiple ways. So you have unconstrained spaces. In many cases, the answer space Z is a space of all tokens, fixed length spans, or token sequences. In these cases, it is most common to directly map Z to the final output Y using the identity mapping. So you fill in, uh, suppose you get a bunch of tokens and you have a prefix prompt, say, then everything after the prefix prompt or everything bit in the closed prompt space is your answer. Then you have constrained spaces. However, there are some cases where the space of possible outputs is constrained. This is often performed for tasks with a limited label space, such as text classification or entity recognition, or multiple choice question answering. To give some example, Yin et al. 2019 manually designed list of words relating to relevant topics: health, finance, politics, sports, etc., emotion, or other aspects of input text to be classified. Sui et al. Manually designed lists such as person, location, etc. for any tasks. In these cases, it is necessary to have a mapping between the answer Z and the underlying class Y, because say you want to you get some emotional word, or say you get sorry emotion some word denoting emotion, say such as joy, but your class labels are positive, negative. You need to have some sort of mapping. With regard to multiple choice Q&A, it is common to use a LM to calculate the probability of an output among multiple choices. So discrete answer search. As with manually created prompts, it is possible that manually created answers are suboptimal for getting the language model to achieve ideal prediction performance. Because of this, there is some work on automatic answer search, albeit less than the search for ideal prompts. These works work both on discrete answer spaces and continuous answer spaces. So you have answer paraphrasing. These methods start with you have an initial answer space Z, then use paraphrasing to expand the answer space to broaden its coverage. So given a pair of answer and output, Z prime and Y, we define a function that generates a paraphrase set of answers. So this is just your paraphrasing function. So the probability of the final output is then defined as the marginal probability of all of the answers in this paraphrase. So this is just a summation. This paraphrasing can be performed using any method, but Jiang et al. Specifically use a back translation. So first translating into another language and back to generate multiple paraphrase answers. So anyone unfamiliar with back translation, I mentioned this earlier also. Say you have a source and a destination, and you get a paraphrased version. So this might be English to French and then back to English. So you have model 1 used here, model 2 here, or even the same model. Then you have pruned and search. So in these examples, first an initial pruned answer space of several possible answers is generated, and then an algorithm further searches over this pruned space to select a final set of answers. Note that in some of the papers introduced, they define a function from label Y to a single answer token Z, which is often called a verbalizer. Shake and Shoots find tokens containing at least two alphabetic characters that are frequent in large unlabeled dataset. In the search step, they iteratively compute a word's suitability as a representative answer Z for a label Y by maximizing the likelihood of the label over training data. Shin et al. Learn a logistic classifier using the contextualized representation of the token Z input. In the search step, they select the top k tokens that achieve the highest probability score using a learned logistic classifier. Those selected tokens will form the answer. Gao et al. First construct a pruned search space by selecting top k vocabulary words based on generation probability at the Z position. by the subsample. So just take the model probabilities over the vocabulary and then the top case. Then the search space is further pruned down by only selecting a subset of those words based on the zero-shot accuracy on the training samples. In the search step, they fine-tune the language model with a fixed template together with every answer mapping using training data and select the best labeled word as the answer based on the accuracy of the def set. So these are just methods which does that. So like in the first paper, in some works, they have a function which takes in label y to a single answer token z, which is called a verbalizer. So in some cases, they find tokens containing at least two alphabetic characters that are frequent in large unlabeled data. So in the search step, they iteratively compute a word suitability for uh, being the representative answer z for a label y by maximizing the likelihood of the label over training data, because you do everything over the training data. And the second one is, as we discussed, you can just use the MLM's probabilities to get the top k tokens. The label decomposition. When performing relation extraction, Shen et al. Automatically decompose each relation label into constituent words and use them as an answer. For example, uh, per city of death is then decomposed. Label words would be person, city, and death. The probability of the answer span will be calculated by as a sum of each token's probability. So again, this is just for relation extraction, specific to I guess relation extraction. Finally, you have continuous answer searches. Very few works explore the possibility of using soft answer tokens, which can be optimized through gradient descent. Hambad Zumian et al. 2021 assign a virtual token for each class label and optimize the token embedding for each class together with prompting token embeddings. Since the answer tokens are optimized directly in the embedding space, they do not make use of the embeddings learned by the language model. Instead, learn an embedding from scratch for each label. So these are some cases. I guess we haven't reached here for prompt ensembling, augmentation, and so on. Okay, so this is all a part of, I guess, this multi-prompt learning. Um, so I guess this video is around half an hour long already. I'll break this down into another part, I guess. So I'll try to cover 6 and 7 in one video and then the remaining part. So 8, 8, 9, and 10, I guess, are pretty just theoretical things, so those could be covered in one video as well. So thank you guys for tuning in. Hope to see you again next time as well. And if there's any feedback, do leave that in the comment section.